Hello, my name is Daniel Blackley and I'm going to be giving a quick presentation on my fourth year's honours project, Cost and Risk Aware Skin Lesion Classification with Bayesian Inference. So let's start off with a little definition of the problem here. The International Skin Imaging Collaboration releases these challenges every year. They also have the largest publicly available skin lesion datasets. And a skin lesion is just some abnormal growth on the skin, which could be a deadly cancerous growth. And we found that the machine learning models are particularly good at classifying these. So the Isaac 2019 challenge proposed an interesting challenge, which was that they gave us 8 different skin lesion classes to train our network on, and then in the testing set, they had a 9th unknown class. And the testing set didn't include labels, so we're not going to be talking about that much in our results. But the idea of the challenge here is we want our network to have some measure of uncertainty so that it can pass on its prediction, or pass on the classification to a human if it doesn't know what it's talking about, pretty much. So we're going to quickly talk about some basic neural network architecture as well. You can see here that we have these nodes here that we call neurons, and this one has 3 input neurons and 2 output neurons, then some number of hidden layers. Here it's just a single 4 neuron layer. And we have these connections between neurons called weights, which use fixed values. So any neuron is going to sum across the incoming weights and then add some bias before outputting that onto the next neuron, which then continues for however many layers we have until we eventually get to our output. And of course, the most obvious way to solve this issue is to just train 10 networks and use variance and entropy across the prediction and just average those predictions. And that's one of the best solutions we have to this problem. But that also requires us training 10 different networks, which can take a long time. So instead, we're going to look at a different method. We're going to use Bayesian neural networks. So Bayesian neural networks differ because instead of using these fixed values, we use a distribution of values. And we call this the posterior distribution over the weights. P of W given D, the probability of the weights given the data. And what Bayesian inference does is it tries to compute the entire posterior distribution for all of our weights, which can be very computationally expensive or computationally intractable, as we say. So instead, what Charles Blundell proposed was his method, Bayes by backprop. Instead of using the true posterior distribution, as you see over here, capital P of W given D, the data, we use our variational posterior, Q of W given theta, and then we try to calculate the KL divergence between these two distributions. And we try to find the parameters of theta that minimizes the KL divergence between the variational posterior and the true posterior. Now, of course, we still don't know P of W given D, so we reformulate this once again into this called the evidence lower bound, or the variational free energy. And the way this works is we sample from each of our distributions. So here you can see we have my variational posterior, and then we have a prior distribution over the weights, which we choose, and we have our probability of the data given the weights, or the likelihood, which is in our case just the cross entropy loss function. And we can try to minimize this function, therefore maximizing the evidence lower bound. So we also have another variational inference method that we want to look at here. We're going to look at both of these compared to just a basic softmax response, but Gal proposed Monte Carlo dropout. So dropout is a popular regularization technique where you drop some neurons in a network randomly. What that means is that you can see that this neuron no longer has any outgoing connections to the next layer. You essentially ignore that neuron for that pass. And what Gal said we should do is, so we use this to train our networks because it's a proven effective regularization technique, then we turn it off and use all of our weights at test time. But Gal says don't turn off dropout, leave dropout on and run multiple forward passes through the network. Then average those predictions and get the variance and entropy, or variance or entropy across those predictions. So you can see that's here, it's just P of Y given X and W, which is the way of looking at our model as just the softmax output of our model pretty much. And then we run 100 forward passes with dropout on, then we average those predictions. So we talked about entropy and uncertainty estimations. An entropy is an information theory metric. It just shows the level of information or uncertainty across some distribution of values. So here we have our, our predictions from our network. We've labeled them P of Y, I, Xi. Essentially, just if we have 8 outputs from our network, I equals 1 is the first prediction we make, I2 the second prediction. And so we calculate the entropy across these predictions for all of our predictions, then we average them across our 100 forward passes, getting the average entropy. So we also need to consider that if we're implementing this in a real world example, that not all skin lesion classifications are equal. That is to say, we can see this cost matrix that we have here. So let's say that we made a prediction for NV, which is on the predictions are on the x-axis, and our true labels are on the y. So let's say we made a prediction that something was nevi, and it turns out it was actually melanoma, MEL. That carries a cost of 150. And now we compare that to something like misclassifying nevi as DF, which only carries a cost of 1. So that's 150 times worse that we've gotten this, misclassified this as melanoma instead of something else. So obviously we want to use our probability distribution to get the expected cost values and then predict using the lowest expected cost. So we have this sum down here, and the lowest expected cost value is the value of j that minimizes the expected cost. So let's say that we have our prediction here. Our prediction are 8 different predictions, and we want to see how costly that is. So we'll look at DF, as we can see here, we're summing across the true labels. So we'll say, okay, well, what's the probability that it's AK? Then we multiply that by this number, and then we say, okay, what's the probability that it's BCC? Multiply that by this number, add them together, and keep going until we've covered the entire row. And we do that for all the rows, and we predict using the lowest expected cost. So each time we multiply and sum across these rows, we're getting the expected cost from our probability distribution. So now that we've gone over all that maths pretty quickly, we can finally look at some results. So here's just showing by forward pass the accuracy. This is sort of to show that 100 forward passes we think is enough to get a good prediction out of our network. And as you can see here, there's quite some variance at below around 20 forward passes, and Bayes by backprop does seem that it's slowly increasing still. But in terms of seeing how well it does over the entire data set, we use a risk coverage curve. So here we have accuracy on the y-axis and coverage on our x-axis. And so the way we've plotted this is at a coverage of 1, we just get the accuracy on the entire data set, and then we find our most confident prediction, remove it, re-get the accuracy, find our next most confident prediction, remove that, and we keep going until eventually we've covered our entire data set, and we get this nice little curve here which shows sort of how the accuracy does across the whole data set. So again, these methods seem very, very comparable. It's very difficult. We can see that, Bayes by backprop seems to perform a little bit worse, especially on the right-hand side, coming to near the end of the data set. But MC dropout and the softmax response seems somewhat comparable. Maybe MC dropout has a little bit of an advantage. We also want to look at our entropy metric. So here we have on the x-axis, we have entropy, and on our y-axis we have the number of samples. So the blue shaded area showing the number of correct samples, and the orange shaded area showing the number of incorrect samples. So intuitively you would expect entropy to be larger for the incorrect samples, as our network is to be less certain. But again, it's somewhat difficult to see that really. It's also somewhat difficult to read because of the number of very confident correct classifications that softmax response and MC dropout both have, but they all do roughly have around maybe perhaps 250 samples is where they peak with their uncertainty estimation at around 0.6. So again, it's somewhat difficult for us to really say which one's better using our uncertainty metric of entropy. But that's fine because we don't necessarily care about accuracy, right? As we said before, we're wanting to have a well-tuned distribution, and we want less costly classifications. So here we look at reliability diagrams which aim to show how well calibrated our distributions are. So that means that within the samples for every time that it makes a prediction. For example, here with melanoma that says 0.2, we expect that prediction to be right 20% of the time. So we grouped all of our predictions into bins here. We have all the predictions within 0 and 0.2, all the predictions between 0.2 and 0.4, and we plot the relative frequency that those classifications occur for that class. It's also important to note then, before we go any further, that we need to look at the number of samples in each of these bins. So you can see here for Bayes by backprop, it's not too bad, but with DF and VASC, the samples can reach barely over 10, and sometimes below 10. And we see this even worse for the softmax response. Again, it's mainly DF and VASC that we see here has less than 10 for a lot of its bins. So we're going to be somewhat skeptical of that and perhaps brush over it. But for the other ones, we can see that for the most part, Bayes by backprop seems to either perform comparably or better consistently. So that means that when we go to look at our cost, we're going to see the expected result here, which is first of all look at cost by forward pass. So the way we're doing this now is we're using the lowest expected cost to make a prediction. Then we're measuring the average actual cost incurred as defined by the cost matrix that we showed earlier. And we can see here that there's a notable difference now. Bayes by backprop performing consistently better and MC dropout also performing consistently better. And once again, we look at lowest expected cost by coverage, and we can see Bayes by backprop across all values of coverage seems to be performing consistently better. And if we break this down by class to get a little bit more intuition, we can see why. Bayes by backprop performs remarkably well on the classification of melanoma, one of the very costly misclassifications. And it's also worth noting here that if our populations change, then perhaps these results could change as well. Because particularly, we notice that Nevi, despite the fact that it is the largest data set, Bayes by backprop, or the largest number of samples in our data set, Bayes by backprop performs worse on this. So maybe if we had if we lived in a perfect world where 99% of people had Nevi and only 1% of people had melanoma, then perhaps it would still be less costly to use MC dropout. But as of just now, in this population using our specific cost matrix, we can see here that Bayes by backprop seems to perform better. So just to conclude, when compared to accuracy, it's difficult to really say, especially when we use our uncertainty metric. There's no clear winner here. Although MC dropout seems to perform slightly better and is easy to implement, so perhaps that should be considered. But if you're considering a cost of misclassification on our specific population with our specific cost matrix, then as we can see here, looking at our cost coverage curves, Bayes by backprop performs better across all values of coverage, even though it is fairly more computationally expensive to run. And this will be the part in the live presentation where you have questions, where I'm sure you do, because this is my 4th time recording this. I've realized that going too in-depth in some of these concepts can keep the time up, so I've had to brush over quite a few things. So hopefully, yeah, when you see me, you'll be able to ask these questions in person. But until then, thanks for watching.